This conference will now be recorded.
Yes, thank you. You people, any new student, like any student present in the session without attending the basics? So everyone are through basics, right? Here, offline. Any new student is there, like without basics? Like some students will directly join the advanced classes. So any one of them like that? Okay. Um, that is the case. If any new student is not there, right, then you people already know what is the people already know how the session works, right? Okay, today here for advanced class demo. So in this session, we are going to discuss about class or course timings, right? How the what is the timings? How the course works for advanced classes, right? Next, we are going to discuss about what is physical design. Already you know because I already discussed the same thing in your uh, first demo classes, right? But still, we'll discuss what is physical design or why physical design. Now, after that, we discuss about our course, what is covered in our course, right? Course structure, what is covered in our course. So these three things we are going to discuss for next 3 hours or 2.5 hours. So at the beginning only, I will start with your course timing or course structure. So our course is structured into two things. One is basics. Another one is what? Advanced. Your basics is already done, right? You have already undergone the basics of Unix, digital, TCL, CMOS, then GVIM, right? That's it. So you've already undergone these basics. So for physical design, most important basics is Unix, TCL, and CMOS. Digital also it's okay, but you should be knowing a very good foundation of Unix and TCL, right? Even CMOS is just important to understand why we do this. If you don't understand, also you can do that. But in day-to-day life, physical design mainly we are going to work with files, most of the files, right? plenty of files operations we do. So understanding Unix commands, like what is command for search and replace, what is command for, see there are basic commands like mkdir, cd, copy command, cp, move command. Those are basic commands. Apart from that, you should be knowing what is grep command, how to use search and replace scd command, how to use awk command. So where we'll use that awk command, how to use it. I have like this, right? 20, and I have some path here, file path. I call it as file 1, 40, file 2, 50, file 3, 10, file 4, 35, file 5, 42, 42, file 6. So like this, you will be having thousands of files. Now I have written only 6 files. Like you will be having thousands of files like this. This indicates some value like slack or something. It's going to indicate. So in this, you have to grep the file which is corresponding to maximum slack. Which file is that? In this example, file 3 is corresponding to what? Maximum slack. Here I can see because I have only what? 6 files. But in the real design, you will be having thousands or 2000 files like this, right? Slack value, file name, or some value, latency value, file name. In that, I am asking you to get the file for maximum value. I don't know, I cannot scroll all the 10,000 lines. I cannot see okay, 20, 40, 50. I cannot scroll all the 10,000 lines. At that time, what command you will use? How do you get that? Either you use a cd command or awk command, any command you use and find this either by Unix or by TCL, tool command language. Even you can do this operation by using Python or Perl, right? So for this reason, physical design we mainly deal with extracting data from a file or extracting data from the tool and writing data to the file. So doing plenty of file operations. So for that reason, knowing Unix and TCL is very important. And CMOS, right? CMOS is just to understand why we do a few steps in the design, right? For that reason, CMOS is very important. And you have already undergone all these basics. So please brush up if you are not up to the mark. So next we go for advanced classes, right? Advanced PD class. See in advanced classes, advance happens for 3 months or sometimes it will be for 3.5 months if we have more holidays. So like this is the period where we have many festivals, Dasara, Deepavali, right? Many festivals we have. If we have holidays in between, it may extend till what? 3.5 months or it will be 3 months course. So your basics was for how many months? How many months over? 2 months, right? Basics is for 2 months and advanced is for 3 months. Totally it is a 5 months course. Sometimes it may extend till 3.5 months. So last batch extended, right? It is 3.5 months. It is extended. So PD advanced class, we have again two categories here. One is lab, another one is theory. First I will talk about theory part. See, theory happens only on Saturday and Sunday. Theory concept is discussed only on what? Saturday and Sunday. Saturday 3 hours, Sunday 3 hours. Right? 3 hours per day. For all the students. It will be probably in the morning 9:30 till 12:30 or 10 to 1, like that. So theory, all the concepts of theory is discussed of physical design, and the lab again is divided into two parts. Lab. I think I've already told this, right? Lab happens on one lab happens on Monday to Thursday. One lab happens on Saturday and Sunday. So this lab is different and this lab is different. Attend any one lab. Generally, if you're available in the weekdays, means some of them are working. They're working in office and they attend only on Saturday and Sundays. If you're available all the weekdays, please attend from Monday to Thursday. It is for regular students. It is regular lab. Saturday and Sunday, it is what? Only weekend lab. It is only for the candidates who cannot attend from Monday to Thursday because some will be working. For them, the lab happens only on what? Saturday and Sunday after the theory classes. The students who are attending Monday to Thursday, they will attend only theory on Saturday and Sunday. After that, they will leave. But the candidates who are attending weekend lab, they have to attend first theory in the morning for 3 hours. Next, after theory, they are going to attend what? Lab in the afternoon. Like 10 to 1, you will be having theory, and from 2:30 to 5:30, you will be having lab. And other students who are attending regular, right? For regular students, the lab happens from Monday to Thursday. It will be 3 hours per day, right? So this is how the structure of PD classes. So this week we are starting with what? Demo. Next week there will be no lab because the theory is not started. Lab will be there only to install the tools. So for the lab, you have to bring your laptop. I think admin will schedule. I think he may schedule on Wednesday or Thursday. They will schedule the tool installation classes. Till now, we have not installed any tools, right? Like you have installed Sigwin, that's it. Any link has been given to install tools? No, admin will tell you how to install tools. They will schedule the classes. I think they'll schedule on Wednesday and Thursday. They'll schedule the classes. So our mentor also will guide you how to install the tools. You have to install the tools to access our software or the tools like ICC2. If you want to use, then you have to start with accessing the tools. You have to start installing the software. So this week, this week means this Wednesday or Thursday, they will start with installing the tools. Next Saturday and Sunday, you will be having what? Theory for all the students. From Monday again, from next Monday, the lab starts regularly for the weekday students, and for weekend students, it happens on Saturday and Sunday. This week there is no lab because already Saturday is gone. Today is Sunday. There is no lab. From next Saturday and Sunday, the lab is going to start for the weekend students. For weekday students, lab will start from next Monday. But this week, so our institute, any of the faculty or any of the trainer will help you with installing the tools, how to install the tools. So you have to install 3 tools. They'll help you, and they'll help you how to open our server, how to access our server. They'll help you with that. So this is how the classes is going to happen, right? Advanced PD classes. And as per your knowledge, you are already getting the recorded videos, right? Everyone is getting recorded videos. For basics, you are getting, right? Similarly, you will also get recorded videos for theory and lab. Live recorded videos you will get after the class completion. that you will get again, even for advanced classes. So for advanced classes, we use synopsis tools. That is ICC2 DC compiler. DC compiler is for synthesis. We use ICC2 for physical design, and star RC for RC extraction. Prime time, we use prime time for STA, static timing analysis sign off. So these are the tools used during the course. Now you can ask me if you have any doubts. So when the advanced lab starts, admin will inform you in the group. So when the lab start, when they are going to install the tools, right, admin will help you in the, he will message in the groups, WhatsApp group.
Sir,
Any doubts you have, you can ask me. Any
sir,
doubts? Yes, please tell me.
I am regular student, sir. If I am unable to attend in regular lab sessions, can I attend in weekend labs, sir?
Yes, you can attend the weekend labs, but the phase of covering will not be the same, right? What
Okay,
topic
sir.
is covered in weekdays, the same topic will not be covered. It means the same, all topics are covered, but the same phase will not be going, right? For example,
Okay, sir.
in the weekdays, floor plan is completed, but in the weekend still they will be doing floor plan. So there will be a variation in the topics done, right? Because same mentor will be there, but it is done only on Saturday and Sundays, right? Some Saturday and Sundays, I think there will be holidays. For example, last Saturday there was a Ganesh Chaturthi, it was a holiday. So because of that reason, the covering topic covered will not be the in the same phase, right? It will vary. So at that time you will get confused, right? So for that reason, I suggest attend either regular lab or weekend lab. Any one lab you attend. If you want to switch, we don't have any problem. Institute is not having any problem. From regular lab, if you want to attend weekend lab, or from weekend lab, if you want to attend regular lab, institute is not having any problem because the fees is same for both.
Okay, sir.
So you can attend any lab you want. You can attend either weekend or you can attend any regular lab. It's your wish. But just ask the mentor that this topic is covered at at that time. You please join, right, when that topic is started. In the weekend, when the topic is starting, you please join at that time. So you will be having continuity.
Okay, sir.
But institute is not having any problem with that. You can join any lab you want. Okay. So now,
Oh, hello.
yes, please tell me.
Yeah. So I want to ask, if course will cover Red Hope also?
Yes. What is? Please repeat.
Red Hope, IR tool also.
No, IR drop theory is covered, right? What is IR drop? What is static analysis? What is dynamic analysis? But tool is not used. We
Okay.
don't have license for that.
Yeah, okay. Thank you.
Redact tool is not used in this course. And IR drop is not part of physical design in the industry also, right? There is a separate engineers for that. Okay, so now this about your course structure, right? Any more queries you have, please contact the admin. So admin will help you with any of these queries, right? Or message in your WhatsApp group. I think everyone are part of the basic courses. You have the individual WhatsApp group. So if you have any other queries, please contact the admin. So next is, what is physical design? What is our course structure, right? So both the things we will discuss now. What is done in our course? What's the course structure? And what is physical design? See, you already know in the basics demo also we have already discussed, right? So in the IC design, we have two things. If IC gets has to be fabricated, right? Integrated. What is IC? Integrated circuit. So when you want to get IC fabricated, you have two things. One is, what is that? Foundry, and one is design. So we engineers work in what? Design. Foundry is responsible for fabricating. They are responsible for fabricating IC. So who are going to work in foundry? Chemical engineers, right? But we engineers work in design, IC design. We are going to do IC design where? By using EDA tools. What do you mean by EDA? Electronic design automation tools. So these are EDA tools what we are using, right? These tools help us to design IC. So these EDA tools can understand only TCL. They cannot understand any other language. EDA tools are built in such a way that they can understand only TCL. What is TCL? Tool command language. These EDA tools will understand only TCL. So we are going to interact with this EDA tool by using what? TCL. By using this, we will design an IC in this EDA tool. EDA tool is nothing but a software tool. It is. After designing an IC, what we will give to Foundry? Yes, for Foundry, what we give? GDS2 file. We are going to give GDS2 file for Foundry. Design team is going to give GDS file for Foundry for fabricating purpose. What is GDS2 file consists of? What is GDS2? Graphical data stream information interchange. So your Foundry is going to fabricate IC based on the GDS2 file. If any problem in GDS2 file, who is responsible for that? Design engineer is responsible. If IC is going to fail, Foundry is not responsible, because Foundry will take care its fabrication process is correct and accurate. If any IC is not working because of the Foundry errors, those IC are thrown out. But IC are not working means what is who is going to take responsibility? Design engineers. So we engineers are going to take responsibility if IC in the market is not working fine. Then what is this GDS2 file consists of? Yes, what is the content of GDS2 file? Yes, what is content of GDS2 file? Content of GDS2 file is layout of cells, right? Layout of cells and its connections. So you know what is layout? You already studied. Everyone has studied layout in your CMOS basics. Yes or no? So what is the layers present in layout? You have P substrate, N well, P diffusion, N diffusion. Gate is formed by what? Polysilicon. You're going to so connection of this layouts of layout of gates is called as what? GDS file. So this GDS file is given to the foundry, and the foundry is going to fabricate IC for us. So means what I can tell, GDS consists of what? GDS consists of layout of ICs. So this is the layout, right? What a layout consists of? This is P substrate. In P substrate, you are going to draw what? N well. This purple color is N well. Right? You are going to draw the N well. So inside N well, what is formed? P diffusion. Here you have what? N diffusion. So in between P diffusion and N diffusion, you have polysilicon. So for CMOS inverter, both gates are what? Shorted. So I will write only one polysilicon. And here you have VDD on top, and at the bottom you have what? VSS. So one side of P diffusion connect to what? VDD. One side of P diffusion connect to VSS. Drain and drain you short. For making connection, you short your gate, and gate you connect to one metal layer, right? This is going to give a contact cut. This is a contact cut. So here one contact cut. Why there is a contact cut here? Because blue color is what? Metal, and this yellow color is diffusion. When diffusion is connecting to metal, I should be using contact cut, right? These contact cuts are required. So this is a layout of what? Layout of inverter. So previous cell, you will be having one more layout here. One more layout. One more layout. So output of this layout, you connect to what? Input. Output of this layout connect to what? Next layout? Input. So this connection of layouts is called as what? GDS. I hope everyone know what is layout, right? Because you already undergone CMOS basics. It's already done. So connection of this layouts is called as a GDS. That is what given to what? that is given to foundry to fabricate IC. So design engineers has much more challenges. So what are the challenges design engineer has to face? Main challenge is complexity. So we have plenty of gates. Crores of gates are present in one IC. 3.3 crores, 4 crores, 5 crores of gates are present in one complete IC. So this much gates putting in one IC, right? That is going to include a complexity. Handling that much complexity is major challenge for design engineers. Then major challenge, one more major challenge is power reduction. Your IC should not consume more power. If IC is consuming more power, your mobile battery will drain very fast. It has to consume very less power. So power reduction strategies has to be included in the design team or during the design of IC, so that my IC is consuming very less power. Can you tell me any strategies? What are the strategies for power reduction? Different strategies. What your laptop is doing when you're not using it? Automatically goes to what mode? Sleep mode. Cut the power to ICs whenever it is not used. Cut the clock. Remove the clock for IC when it's not used, so that IC will stop consuming the power. So that is called as power gating. Cutting the power is called as what? Power gating. Cutting the clock is called as what? Clock gating. So those type of power reduction techniques has to be used, so that my IC has to consume very less power. That is a challenge for design engineers nowadays. How to implement power reduction techniques. So next is high speed of operation. Here high speed of operation means it is clock frequency. What is clock frequency we are using? What clock frequency? We are using clock frequency in the order of what? Gigahertz, right? Earlier it was in megahertz. Now we are working with what? Gigahertz. 1 gigahertz or 2 gigahertz clock we are using. So we have to see that our IC is working with this much fast clock. So high speed of operation is major challenges implementing this high speed of operation. Next is area. All this 3 crores of cells should be integrated in very small area. IC is only this much size, right? What is the size of IC? IC size is only this much. This is the size of IC. In this IC, we have 3 crores of cells. So putting 3 crores of cells within this small size is really challenging. So we use and working with lower technologies. We work with lower technologies like 7 nanometer, 4 nanometer, 3 nanometer. Technology is very challenging for us. So what do you mean by 3 nanometer technology? If I tell technology is 7 nanometer, what is the meaning? Yes, sir. Channel length is only 3 nanometer, right? Distance between source and drain is only 3 nanometer. If I tell we are using 4 nanometer technology, what is the meaning? We are using the transistors where distance between source and drain is only 4 nanometer. So reducing the area by implementing lower technologies is very challenging for us, because new rules come into picture when we use lower technologies, right? We have plenty of DRC rules. So next is implementing DRC rules. See, foundry is going to fabricate IC for us. I have to follow the foundry rules while designing, because ultimately foundry is having the machineries. What are the foundry rules? What are the rules given by foundry? We have to follow that. Then only my IC is fabricated properly, or else my IC will not fabricate properly, right? So I can tell follow the DRC rules given from foundry, DRC rules and design for manufacturability. DFM, design for manufacturability. There are rules and guidelines to be followed while designing an IC. Then only my foundry can fabricate the IC properly, or else my foundry cannot fabricate the ICs. So these rules are very challenging for us, because at lower technology we have many rules. So implement all these things along with what? These rules is very challenging for design engineers. This challenge what we are talking, right? The last challenge. Follow the rules given from foundry. Majorly it is applicable for PD engineers. We only have to follow these rules. Front end engineers will not follow these rules because they are working in front end. They're not working at layout level. We are working at layout level. We have to follow these rules. So major challenges for us is following the DRC rules given from foundry, right? So all these are major challenges for design team. So by facing these challenges, or by implementing all these criteria in our design, we will create a GDS file, and that GDS file is given to what? Foundry, and foundry will fabricate IC for us. So while using what is this EDA tool? EDA tool is a software tool, right? This EDA tool, along with this, the design engineers they should have additional capability. What is that? EDA tool is software tool. So we should be knowing how to use EDA tool, how to use ICC2, how to use star RC, right? How to use prime time. We should be knowing that. So today you are working in one company. That company is using ICC2. Tomorrow you are doing the project of some other company. They are using Innovus. Innovus is a cadence tool. So ICC2 is different. Innovus is different. Because all the industries what are present in market, they use both the tools. Some company uses Innovus. Some company uses ICC2. Now the question arises, right? How to use this EDA tool, right? You have to learn that. Next, interacting with EDA tool, TCL. So we can interact with EDA tool only by using what? TCL. Only TCL is not sufficient. TCL is a basic language which is required. Compulsory should be knowing that. If you are a PD engineer, compulsory should be knowing what? TCL. Without TCL, you cannot do physical design. But TCL only is not sufficient, because while using EDA tool, we work on many files. I gave an example at the beginning. To do this file operations, to implement automation flow, along with TCL, you should be knowing Python or Perl, right? If you know that, it's added advantage to you. You can do the physical design, or you can implement physical design in better way if you know Perl and Python. It's not a compulsory you should be knowing it. If you know, it is good. But TCL is compulsory. You should be knowing that. Because same file operation can be done using TCL, same file operation can be done using what? Python. Both is having large difference. Python we can do file operations very easily compared to TCL. In TCL also we can do. I think you already learned in basic courses. But in Python we can do it in better way. And all these EDA tools, what we are discussing, they are installed in Linux operating system, because it is very effective and robustness, right? They are installed in Linux, so you should be knowing Linux commands. File operations even I can do by using TCL. Even I can do by using what? See, you have a file where in one column you have a files in one column you have clocks, right? You have clock in one column. You have 50 clocks. For the 50 clocks, in next column you have latency. Next column you have skew. In next column you have max trans violation. In next column you have max cap violation. In next column you have clock period. You don't want all these things. You want only the clock name. You want only the time period. What is the time period? All these intermediate columns you don't want. Right? You want only the clock name and you want only what? Time period. Then how do you do that? How do you remove this intermediate columns? Entire columns, right? Has to be removed. How do you do that? Which command you use for this? Awk command, right? So like that, you will be doing plenty of Unix operation. So these are the challenges for us, right? Again, so to learn different EDA tools and TCL mainly for automation. Automation, you should be knowing TCL and you should be using what? Linux command. You have to do automations. So by doing all these things, we give what? GDS to Foundry, and Foundry is going to fabricate IC for us. So Foundry can understand only layout. But design, our IC design starts with what? ASIC design flow. Our IC design, see this is very important question in industry or in the interview. Explain ASIC design flow. Very important question it is. Foundry can understand only GDS. But design team is going to give GDS for Foundry. Design team will start the design from what? From where they are going to start the design. So okay, specification ignore. After specification, RTL design, right? We are starting the design with RTL code. At least you should be knowing the basics of Verilog. You know that basics means just how the RTL is present, like module name, input. That is not done. Okay, I'll ask admin to do at least if possible next week, just one class of Verilog. Okay, ASIC design flow. ASIC design flow, it starts with specification because I already done all these things during your basic courses. I'll ignore specification. So we start with what? RTL design. In RTL design, we use what? Verilog or VHDL to start with our design. So why we start with Verilog or VHDL? Because Verilog or VHDL will help us to describe the circuit based on its behavior, right? I always take this example, like if you want to write because it's a simple example, right? So your RTL, if you want to write RTL for mux, 2:1 mux, this is 2:1 mux. 2:1 mux has what input? I naught, I1, output Y, and select line S. So if you want to write the Verilog code, how we are going to write? Module name, any module name you can use. Module name I will use it as temp. What is the module name? Temp. Then what are the inputs? I naught, I1, Select line is Y. First you declare the inputs. What are the inputs here? I naught, I1. Yes, yes is the select line. What is the output? Next, you can implement this in any ways. If you can implement this in if statement, or you can use a boolean expression, or you can use a case statement. I write if statement. If select line is equal to 1, then y is equal to what? Y is going to take this if statement. I cannot write without always block. First, I should use what? Always. Always at star. Star means you consider all the inputs. This always block is going to work if all the any one of out of these three input, any one input is changing. This always block is going to work. So always block will start with what? Begin if select line is equal to 0, right? Y is going to take I naught, else Y is going to take I1. Next, end the always block. Next, use what? End module. So here you are describing the mux based on its behavior, right? You are not describing the mux based on its internal structure. You are not at all worried how this mux is formed. This mux is formed by using AND gate, and NOR gate, and NAND gate, and XOR gate. You are not at all worried. You are not worried about its internal structure. You are worrying only about its behavior. Like y is equal to s is equal to 0, y will take what? I naught. If s is equal to 1, y is going to take what? I1. So this is a behavior. When you are worried only about this behavior. So by using your in RTL, you describe the design based on the behavior, right? Describe the design based on behavior. So this behavioral description you cannot give to Foundry. Foundry requires what? Layout of cells. Cells means gate, right? So what you have to do is convert this RTL to gate level netlist. But after RTL, there is one more team called as what? Design verification team. DV. DV stands for what? Design verification. So what is design verification team will do? Verify functionality of design, right? Verify functionality of design by applying test cases. You apply different inputs, right? Here also for mux you apply different inputs, verify what is output. So for mux you apply select line, you have y, you have select line, you have I naught, you have what, you have I1, you have, and even you have y output. You apply 0 0 0, what is output you will get? If select line is 0, y is going to take what? I naught. So what is I naught? 0, right? Y is going to take 0 0 1 0. 1. The S is equal to 0, y is going to take I naught. What is value of I naught? 1. 1, 1, 1. 1. Because when select line is 1, y is going to take what? I1, and I1 is 1. 1, 1, 0. 0, right? Now select line is 1, y is going to take I1. I1 is 0, this is 0. So this is called as test cases, right? This is one test case. This is called as what? Second test case. This is called as what? Third test case. So apply different test cases and verify the functionality of design. That is called as what? Design verification. So to do design verification, they will learn system verilog and UVM. So this RTL, whatever we have, it is in the behavioral form. This is just a verification of RTL, right? If RTL is working fine, then it's done. But we have design in what form? Verilog or VHDL, it's in the behavioral form. That we have to convert into layout form. Before converting to layout form, we convert into what? Gate level form. That is called as what? Synthesis. So what is synthesis? Converting, is RTL to gate level netlist. This is called as synthesis. So what is synthesis consists of? What is the inputs for synthesis then? What are inputs for synthesis? So inputs for synthesis. You are not going to do synthesis. Your tool is going to do synthesis, but you have to give the right inputs, right? So first input for synthesis is your RTL, because RTL only it has to convert, correct? So RTL is in what file? .v or .vhd. It's a Verilog or VHDL file. So RTL is one of the input for logical synthesis. Second one, what is the input? Yes, library files. See this library files. In the advanced classes, we are going to open this file, Liberty file. We are going to understand each and every line present in that, how it is present, what is present in that. We are going to do that from the next week. We'll start with this input files, right? We will open these files and we'll see what is present in that. From next Saturday class, I am not going to do this. We are going to do with some concepts of CMOS brushing, right? Like what is delay, what is power consumption. It's already done, right? CMOS it is done, right? Cell delay, different type of power consumption. What are different types of power consumption? Static power and static power as leakage power, dynamic power as switching and short circuit power. So this concept is already done. So I am going to tell how this concept is applicable for our physical design and what are different types of cells based on this concept. So next week I will do that, and from Sunday I will start with input files. And input files we are going to open, because you should be also opening these input files. You should also see the input files. So library file will open and we'll see each and every line, what is present in that. So library file is also called as what? Library file is also called as Liberty file So it is what is the extension for that? .lib. What is .lib as? The basics class is done for you. Basics class. PD basics is done. No, okay, I'll do that. This liberty file, what it has? In one word, if in interview they ask what is the content of liberty file, how do you tell in one word? Hmm? Liberty file has area, power, and timing information of standard cells. Timing means what? Delay, right? Cell delay. Cell delay is called as what? Timing. So this information is present for standard cells. Then what do you mean by standard cells here? What are called as standard cells? So standard cells are the cells which are already designed and tested. And standard cells are the cells which is compulsory required. These cells are compulsory required to implement any circuit. What are those cells? Inverter, buffer, OR, and NAND, NOR, XOR, MUX. See, if XOR is all not present, no issues, right? Because we can implement XOR by using these gates. MUX, apart from MUX, D flip flop, and latches. So these are the basic gates which is required to implement any circuit. So these cells are called as what? Standard cell. Your .lib is having area, power, and timing information for all these cells. So next class we open this file. We'll open and we'll see the file, right, in the next class. Next, one more input file we want. What is that? SDC file. SDC stands for what? Synopsis Design Constraints. So what this file consists of? It mainly consists of clock information. So in your design, what clock is present? What is the time period of the clock? Right? Clock information, clock uncertainty, clock transition, set input delay. Right? It has set input delay. It is for I/O constraints. Set output delay. Set driving cell. Set load. Clock uncertainty. PVT conditions. RC corner. So all this information is present in SDC, but you will not understand now anyhow these terms, because to understand these terms we have to go to the advanced part. So in advanced part we see what is the meaning of each term and how to define it. What are the commands to do that? How to define clock information, right? So just I'll give one example how to define clock information. So we have a command called as what? Create clock. Create clock is going to create the clock. Give one name, minus name. You can give any name for the clock. I will give clock name as what? MCLK. This is a clock name. Minus period. What is the time period? 1 nanosecond. What is the time period? If the clock is 1 gigahertz, frequency is 1 gigahertz, how to find time period? Time period is equal to 1 divided by 1 gigahertz. I'll get 1 nanosecond. Next, where it is starting in my design, from which port from which port this clock is coming in my design, right? I have a port in my design. This is a port. Through this port, the clock is entering to my design. What is this port name? In RTL, you have defined port names, right? So through which port this clock is coming into my design, I have to define that. Get ports CLK. Just I gave an example, right? This is one of the example to define what? Clock. So this clock is coming to your design through this port and it's connecting to flip-flops and latches. So what is the time period of the clock? 1 nanosecond. What is the name of the clock? M clock. So which command is going to create this? Create clock. So like this, for each thing, what is a command? So we are going to see that in the advanced class. How to write this SDC. So SDC has these many parts. Then what is output of this? Yes, what is output of synthesis? Gate level netlist. So this is an example for gate level netlist. So next class, even in the advanced class, even we open gate level netlist and we see that how the gate level netlist is defined. This is example for gate level netlist. So first I will write how this gate level netlist is present. Then we see remaining things, right? Gate level netlist, how it is represented. You assume that this is the design, right? This design at the beginning, it is having a port, input port. The input port name is what? M. It's also having one more input port. The input port name is N. It's having one input port. The port name is clock. One port it's having, its name is what? Reset. So all this. So input and output of this entire design is called as what? Block ports. Input and output of the entire design is called as what? Ports. So what are the ports here? M and clock and reset. So this is going to one AND gate. M and N is going to what? One AND gate. So AND gate is having A pin B pin, Y pin. Input and output of the gates is called as what? Pins. So this A, B and Y is called as what? Pins. But M, N, clock reset is called as what? Ports. Input and output of a block or input and output of a design is called as what? Ports. But input and output of a cell is called as what? Pins. Here A, B, Y are called as what? Pins. And output of this pin is going to one flip-flop. This is D flip-flop. So clock pin is connecting to this D flip-flop is having clock pin. Its name is capital CLK. It's connecting to the clock port and it is having reset. It's connecting to the reset thing. Whatever Q I am getting, right, output, it's connecting to one inverter. This inverter is having A pin, Y pin, and it's connecting to the output port, and this output port is O port. You assume that this is a simple netlist what you got, or simple gate level diagram what you got, for simplicity, right? Then how to write the netlist for this? So this intermediate signals, right? This intermediate signal is called as nets. This is N1 net. What is this? N2 net. How to write the netlist for this? So netlist is also a Verilog program or VHDL program. So Verilog starts with what? Module name. I will take one module name as temporary, right? Temp. So first we have to declare what? Inputs. What are the inputs? M, N, clock, reset, O. Next I have to declare all the inputs. What are the inputs I have in my design? Input. What are the inputs? M, N, clock, reset. Next I have to discuss what are the output. Output is O. Wire. What are wires? N1, N2. Intermediate signals are called as what? Wires. Next, I have to discuss each cell. So, what is a cell name in the library file? Cell name. This cell is having a cell name. For example, in the library. Library means what? This .lib. Right? This library. In this library, the name of this AND gate is AND 2 with x2 drive strength. Drive strength means how fast it can. What is a cell delay, right? X2 means it's having less cell delay. X1 is having more cell delay. So this is what I am going to discuss in next week. What is X2? What is X4? What is HVT? What is LVT? What is RVT? That we'll discuss in next week. Now for the time being, you understand that X2 means less cell delay. X1 means more cell delay. So this is what the name present in .lib. For D flip-flop, the name present is DFF AR. AR means asynchronous reset. This reset is asynchronous pin. AR X2 drive strength, X1 drive strength. This is the name of the flip-flop present in what? .lib. Inverter, right? The name of the inverter present in .lib is in INV X1. This is the name present. Then first I will discuss about AND gate. So AND gate, what is the instance name? What is the library name? Library cell name? And so I have written only AN, right? It's AND, AND. Yeah, AND gate, 2 input, X2 drive strength. This is the name of the cell present in library. Your synthesis tool will give one instance name. Instance name of this is U1. What is instance name? U1. Why this instance name is given? Because each cell should have different name, right? Because in the design I can have 10 AND gates. All the AND gates library name will remain what? Same. So one AND gate will be having instance name U1, another AND gate will be having instance name U2. So different cells are given with different instance name. My synthesis tool will give this. So here instance name is what? U1. Next, port mapping. What is the port mapping? A pin of this AND gate, where it is connecting? M port, right? A of M, comma, B pin, where it is connecting? N port, comma, Y pin, right? Where it's connecting? This Y pin is connecting to N1 net. N1. Next, what is the next cell I have? D flip flop. So the D flip flop name DFF AR X1. What's the instance name? U2. This instance name is U2. Next to what? Port mapping. Port mapping means where this D pin is connecting to. Where this D pin is connecting to? N1 net. Where this clock pin is connecting to? This clock pin is connecting to clock port. This is in capital letter, this is in what? Small letter. So where this reset pin is connecting to? Reset is connecting to reset. Where Q is connecting to? N2, right? This Q is connecting to N2. But D flip flop will be having one more pin. What is that? Q bar. Q bar I am not using it. So what happens here? QB, it remains what? Unconnected. Your tool will mention it as what? QP, which is unconnected. Because I am not connecting QB, I am leaving as it is. I am not using that pin. But when I get the D flip flop from the library, in the library itself I will be having this D pin, correct? From the library I will be getting this D pin, sorry, QB pin, sorry. From the library, when I get D flip flop, in that QB pin is already present. This QB pin is, I am not at all using it. So what we do? QB unconnected. So we will leave unconnected. Next, what is the next cell? Inverter with what? X1. So A pin. So instance name. What's the instance name? U3. You have dot A where A is connecting N2 and dot Y where it's connecting O. Next do what? End module. So this is called as netlist. This netlist has gate and its connection. That's it, right? It is not having any if statements. It is not having any assign statement. It's not having any always block. It's not having any case statement. It should be having only gates and its connections, right? Here connection is maintained because N1 is connecting output pin of AND gate and the same N1 net is connecting what? Input pin of D net. This indicates that output of AND is connecting to what? Input of D flip flop. Here also, right? N2 net is connecting output pin Q pin of D flip flop. The same N2 net is connecting to what? A pin of inverter. This indicates that output of D flip flop is connecting to what? Input of inverter. So what is gate level netlist? Gate level netlist has gate and its connections. That is called as gate level netlist.
इधर हम सब कुछ डालना पड़ता है तो हम क्या लेते हैं इजी लेने का स्पाइसी चाहिए तो
Any doubts you have? If you have any doubts, please unmute or else please mute it. Right? If you're unmuting and if you don't have doubts, please be silent.
इसलिए मैं बोल रही थी थोड़ा सी
So I am muted. If you want to have any doubts, you can unmute. Okay, this is about your synthesis. What is output of synthesis? Gate level netlist. It is like this. So here also you can see I have shown one example here, right? This is a gate level netlist. What is this? Inverter X1 RVT. What is that? That is a inverter name present in library file or .lib file. What is U21 instance name? What is this port mapping? A pin is connecting to what? Net N21. Y pin is connecting to net N20. What is this? NAND 2 indicates a 2 input. X0 indicates X0 drive strength. I will tell you what is RVT everything next week. Why RVT is what is HVT, what is LVT. What is the instance name? U24. A1 is connecting to N18 net. A2 is connecting to count 4. This is a port name. Count 4 is a port name, right? It's count. It's 7 down to 0. Means count 4 means it is a port name. And it's connecting to what? Output pin is connecting to net N17. So this is a real net list we got from the synthesis tool. Same thing even I have written. But this netlist has how many cells? These many cells. Right? One after other, each cell is declared. Next, after this one, synthesis, one more team will come into picture before physical design. What is a team called as? DFT team. Design for, see, we will do the synthesis in our advanced class. We will do the synthesis in hands-on. In tool we are going to do that. Hands-on will be done for this. You will open the synthesis tool and you will do the synthesis of the RTL. You will obtain this gate level netlist. We will not do at the beginning because for after doing synthesis doing is just a half an hour work. But after doing synthesis, you should be analyzing the reports, gate level timing reports. You cannot analyze timing reports till you do STA. There is a concept called as STA. What is STA? Static timing analysis. That we want at least 1 month has to be completed. Even to do STA, we want some basics has to be known. Like what is floor plan, what is macros, what are ports. So first we start with physical design. Because to do physical design, no prerequisite is required. Like STA and all is not required. You can start with floor plan. So when you start with floor plan, in the theory, meanwhile we also complete with STA. So when you come to the placement, you need STA. At that time, you would have already completed in theory. What is STA? So you can do placement, you can do CTS, you can do routing. In the last, we do what? Synthesis. Because synthesis is just half an hour work. This work is half an hour work. But analyzing the reports, timing reports, you require the knowledge of what? STA. So if I start from the next week, you will not be having that knowledge. Even to do STA, I need at least 1 month. Means like 4 weeks is required to complete that. So for that reason, we do at the last. So what is this DFT? Design for testability. What this team will do? Design for testability team. What? See your chip, right? Chip is fabricated. It has to be tested whether chip is working fine or not. See, when chip is tested, they cannot use this chip directly in laptops, or they cannot use the chips directly in phones, because during foundry fabrication also they will do mistakes. Fabrication mistake happens. Sometimes metal layers are not right. Sometimes these metal layers are not fabricated properly. Right? This is the actual metal layer I want to be fabricated, but during fabrication the metal layers are fabricated like this. So without knowing, both are what? Shorted. Every IC this will not happen. In few ICs it may happen. Out of 100 ICs, we see this problem in minimum 40 ICs. Only 60 ICs will work properly. 40 ICs are thrown out. And some ICs will be having performance issue, power issue. Some issues will be there in an IC. Means immediately when IC is fabricated, it has to be tested. So okay, IC come out. How do you test? If this IC is for mobile phone operation, whether this IC you will incorporate in mobile phone and you will test? No. How do you test? For testing, you will apply. See, you will be having some test port. You will be having some test out port. You will apply some vectors in test port. Vectors means bits. So these bits you will get from what? Output ports. You will verify with the previous recorded values in software, whatever you recorded, right? In software, you compare with that. If both are correct, then what you do? You tell that this IC is working fine. If both are not correct, you will throw this IC. It's not working fine. So to facilitate this operation, passing the test vectors, getting the test vectors at the output side, to facilitate this operation, DFT team will add some additional cells in our design. Those cells will not affect functionality. Just they are going to help in testing the ICs. See, they are going to add those cells during the design phase. That is going to help the IC for what purpose? Testing after what? Fabrication. Testing IC after fabrication is called as what? Post silicon validation. Testing IC after fabrication is called as post silicon validation. So DFT team, what they will do? They will add some additional logics. Logics means cells in design. See, please be silent, right? That last second when you are talking, it's audible till here. Add some additional logics in design to test IC after fabrication. So they are going to add some. So we will see how they are going to add. What is scan chain? We are not going to see DFT, but knowing at least what DFT will do is required even for physical design engineers. So what are scan chain? How the flip-flops are connected in scan chain manner? How scan chain is going to help in testing IC? That we will see in advanced process. So how this scan chain has to be taken care? During STA we have to create two modes. One is functional mode, one is what? Test mode to do timing analysis. So at that time we will see this, what this DFT team will do. After DFT, there comes a team called as what? Physical design. So we'll take a break now. Now time is 11:40. take a 15 minutes break, right? So we'll continue again at 11:55. Take a break. So we'll continue this physical design after the break. So physical design will just discuss what are the topic covered in this course. See, we are not going to do DFT because DFT is a separate course for sure. It's again a 3 months course for DFT. But just we see in one class we see what DFT will do. Just a brief introduction. It is not today. In the future classes we are going to see this. But this synthesis we will do hands-on. We will do hands-on for 2 days. Compulsory we do this. Hands-on means you are going to use DC shell. That is a tool for synthesis. We are going to do synthesis also by using tool. Next, this is part of our course structure. And next we see what we do in physical design, what is covered. Right? That we are going to see next. After that, I am available for your queries. Then we will close. Right? Okay. Come after the break. Yes, we will continue now. So physical design. So physical design always starts with partition. What is partition? See, there is a full chip. Full. We cannot do direct physical design for full chip because full chip will be having cells in crores, right? The entire this is a full chip. This is called as core area. This is called as what? Die area. This is core area. This is die area. See, doing physical design for a full chip is very difficult because the cells will be in the count of how many cells I have seen in this example, previous example, 1, 2, 3. But these type of cells you will be having in crores. So you cannot do direct physical design for crores of cells. So then what the engineer will do, he will divide his entire full chip into different blocks like this. This is one block. This is another block. This is next block. This is another block. This is one more block. This is some other block. Some other block. Right? So entire chip is divided into different blocks. This is block A, block B, block C, block D, E, F, G, H. So each block is given to each engineer. So one IC, entire IC, bigger IC, they split, right? Minimum they will split into 40 blocks. I'm talking about big ICs, which were the companies like Qualcomm, Intel, AMD, Nvidia, they're working. The big block, they minimum split into what? 40 blocks. So each engineer, you start doing physical design for what? Each block. For your block, he will give what is a netlist, other files, what are required. For each engineer, they'll give separate netlist, right? So now what you do the physical design for your block. For example, the person C, what is his shape? What is the shape for person C's block? This is a shape, right? This is a shape for what? Person C. So now you create physical design for this C block. The engineer will create a physical design for C block. A engineer will create physical design for what? A block. After doing physical design, all the blocks will be taken from this full chip level, and full chip level engineer will integrate all the blocks. This full chip level engineer is called as a chip top. What is called as chip top or SOC engineer. Not only one person, there will be some team. Chip top team will be there, or SOC team will be there. So they will take care about this, integrating all the blocks to form entire IC. So now, first 4 to 5 years or 6 years, you will be working in which design? Block level design. Later, when you become experienced, then you will move to what? You may move to SOC level, or you may be working in still block level, like other teams, like STA team, or in some other teams will be working. But when you go as a fresher or with 2 years or 3 years experience, you work with what level? Block level. They'll give block level. If you are 4 years or 5 years, still they'll give block level, but they'll give some complex levels. See, here only you can see which block is complex. See, H is not complex, right? A is not complex because they are having what shape? Rectangle shape. But your D is complex, right? It's having which shape? Inverted L shape. You can see the shape of D. This is a shape of D. Inverted L shape. And all the blocks may not have same cell count. This may be having cell count of 2 lakhs. This may be having cell count of 5 lakhs. This may be having cell count of 4 lakhs. This may be having cell count of 30 lakhs. This may be having cell count of 20 lakhs. This may be having cell count of 1 lakh. This is having 50,000 cells. This is having 15 lakhs. So this block is very complex. Why? It is having 30 lakhs. Even the block is given to the engineers based on their experience. So very good experienced engineer will get what? More cell count. Engineer who is having less experience will get what? Less cell count. Even if you are lucky, you will also get the block with is having just 10,000 cells. 5,000 cells also you will get. Like that is called as feed through, or it is a channel partition. Right? Even you will also get, there will be a blocks, simple channel partition blocks like this here. This is very small block. Here. This is just having 5,000 cells. Even you may get this type of blocks also. So, but experienced engineers will get what? High complex blocks. So now you will do physical design of a block level design, right? We are going to do. So physical design starts with what? Physical design starts with the partitioning, where entire chip is divided into blocks. So we are doing block level physical design. So in block level physical design, first starts with what? It starts with floor planning. Floor planning means creating this core area and die area, right? This core area you have to create, and boundary you have to create this boundary. This die area is also called as what? Boundary. Design boundary. Generally at the block level we don't call it as die area, we call it as what? Design boundary. This is your core area. This is die area, but the block level we don't call it as die area, we call it as what? Design boundary. So in the floor planning, first what we see is we start with creating core area and die area. We see how to create this core area and die area, what are different commands. See, you are not going to create the core area and die area. Block level engineers will not create this. Who is going to create it? Full chip level engineer is going to create it, right? Because for C, this is the design boundary and this is the core area. He has to create this. You cannot create this, correct? Who is going to create this? Full chip engineer or SOC engineer is going to create core area and die area for you. Whatever he is created, you should use this. Sometimes he may ask you to create. You create core area and die area with this coordinates. This coordinates he will give. This x coordinate, y coordinate. These coordinates he will give. All these coordinates he will give. By using these coordinates, you create it. So how to create this? What are the commands to create this core area and die area? What are different commands we have, different options we have? So all those things we are going to see in what? Advanced physical design. Next, what is the next step? Port placement. So port placement means input and output of a, see what are the ports present here in this example, M, N, clock, reset and O, right? These ports are logically described, but physically they are a metal layers, right? We have to place these ports in between this die area and core area, right? I have to place the ports here. All the input ports I will place here. My chip top is telling, right? Place all the input ports here. Place all the output ports somewhere here. So I have to follow my chip top. Who is telling? Based on that, I have to place the ports. These ports are simple metal layers. What are they? They are simple metal layers, metal pieces. So now, Y is telling to place few ports here. Y is telling few ports here based on the communication. For example, your C port is communicating with G, right? You assume that C is communicating with G. All the outputs of G is carried by what? C. All the outputs of G is carried by C. So all the input ports of C should be placed here, correct? Because output of C, it will directly carried by what? Output of G is directly carried by C. So all the input ports of C you keep here. And output from C will go to which? What? F. Then all the outputs of all the output ports of C you place at the bottom here. So it can directly go to what? F. So based on this block connectivity, he will tell where to place the ports. So based on these guidelines, how to place the ports? What are different commands to place the ports? So we are going to discuss, right? Here we have example here. You can see this. These are the ports. These are the ports. This is a net. Right? This is a port. Just with a piece of a metal layer. This is a port. So all these ports, all the input ports we have placed on the left, all the output ports we have placed on what? Right, and clock ports are placed on top. So you can see die area and core area. What is this? This is design boundary. And what is this? Core boundary, but it is not visible there, right? You can see the line there. This is core, and this design boundary. Two boundaries are there here. One is design, one is what? Core. This is core and this is design. Both are present here. So after this, you will do only port placement. Ports are placed like this. Left side input ports, right side output ports. Top we have placed clock ports. So how to place the ports? We'll see. Right. What is the next step? Macro placement. What are macros? Apart from standard cells in our design, we also have what? Macros. Next is macro placement. See, macros are complex cells which are already optimized. Macros are complex cells which are already optimized. Optimized means already designed and optimized. Already designed and optimized. So these are called as macros. So macros are complex cells, they are not standard cells. Already the layout of macros is available, already layout of SRAM is available. Why I have to write RTL code or I have to do synthesis? Alright, not required. Already directly I use a layout. Alright, if layout of any cells are already present and if you want to reuse that, right, then you can directly use those things. So these are macros. These are complex cells, layout of complex cells, right? So inside this you can see the layout present. If all the layers are available, you can see. So it is layout of complex cells. Place that first. Means the layout is already available. Why I will write the standards? Why I will implement this SRAM from the level of standard cell? I'll directly reuse the layouts. So now we will discuss what are the guidelines for placing the macros in the advanced classes. How to place this? However, I cannot place that. There are some guidelines. You can see all these macros are placed from what? Core area. They are not placed in the middle. What are the guidelines? How to place them? So these macros generally in a design, right? They will vary from 10 to 100. Generally, it will be in the range of what? 10 to 100. Some designs may be having 10, some designs may have 20, some designs may have 40, some designs they may have 70, some designs may have even 100. It will vary from 10 to 100 generally. Some rare designs may have 120, 140, 180 in rare case, but in general case that will vary from what? The macro count will vary from 10 to 100. So for that reason, we'll do macro placement first. So after macro placement, we do power planning. Power planning means we will create the VDD and VSS rails like this, right? So these are called as traps. I use only M8, right? This is VDD. What is this? VSS. VDD, VSS. We'll create a straps like this, and after that we create a rails, right? So we will see how to create all these rails, straps, everything. These rails are not seen. So why power planning is done? Because all the cells, standard cells, all the macros requires VDD and ground, right? This VDD top and bottom out, it is having what? Ground. So external VDD and ground should come and connect this, right? External VDD and ground should come and connect to this. Every cells require this connection, VDD and ground. So to give VDD and ground connection for all the cells, we do what? Proper power planning with less IR drop. So what is IR drop? How to do all these connections, how to do the power planning, how to create the straps, right? So we have straps here. So this is horizontal straps. This is VDD, this is VSS. You can right click, go to properties, you can see here. What is this? VSS. What is this? VDD. So VDD, VSS, VDD, VSS straps are created. Similarly, horizontally also created. VDD, VSS, VDD, VSS, VDD, VSS. This will connect to the rails. So how to plan everything, all these things. We will see it in what? Power planning. So after this power planning, so next step is what? See, next in our course we do STA. After floor planning, we do what? STA. In STA, we cover topics like what is setup and hold, into reg and reg to out, paths, PVT conditions, latency, skew and jitter, multi-cycle, half cycle path, and half cycle path. So all these things are covered in what? STA. So we after immediately floor plan, we do STA. This is completely theory because STA concepts are used after what? From the placement stage. But in the flow, after floor planning, what is the next step? Placement. But after this, I will in the theory I will be doing STA. In the lab, you will be just learning how to what are the files, right? I told there is a STC file. What is STC file? How in STC file how these are declared, right? They will be discussing that. I will be doing STA in the theory, and the lab in the lab they will be discussing about STA file, MCMM file, how the PVT conditions are declared in files. So everything will be declared. Everything will be taught parallelly. So during the placement stage, what is placement? Place all cells inside core area. So how to place all the cells inside core area? What is the command for that? What checks we do after placement? So we do checks like max trans and max cap, setup, and hold, congestion. So hold will not do after placement. Setup analysis. Setup analysis, you are learning from what? STA, that you do here. So all these checks we do after placement. How to do all these checks? How to validate your placement stage is correct or not? It is in a good state or not? So what everything you will learn in placement step. Right? After placement, you can see that your cells are placed inside the core area. You can see all these are cells. All these are what? Layout of cells. What are this? They are not simply cells. What is this? Yeah, that is not seen. We have disabled the visibility. If I enable, you can see. Disable the visibility means we have removed all the visibility. Okay, if I disable the routes, everything is going. I will disable only signal routes. So you can see this is a layout of a cell. So this layout, what is this? This is a cell, right? This is one cell. Inside that you are seeing metal layers, sir, but you're not seeing other layers because it is disabled again. If I enable everything, you cannot see the cell at all. So if I enable everything, you cannot see that at all. What is this? This is NVEL, right? What is this? NVEL. So inside this is a layout of a cell. Whatever we are seeing here, what is this? These are all layout of a cells. This one cell, this another cell, this next cell, this cell, right? All cells are placed here inside the core area. So it's placed like this. So we'll see how to place all the cells. What are the checks we do after placement? So after placement, what we have? CTS. What CTS stands for? Clock tree synthesis. So we see what is CTS. Why CTS? Why clock tree synthesis? What is CTS? Build a clock tree. Build a clock tree by using inverters and buffers. That is called as clock tree synthesis. So build the clock tree by using what? Inverters and buffers. In between you add inverters and buffers and build the clock tree. Why we have to build a clock tree? And what are the checks after CTS? So all these things we learn. This very crucial step in physical design, factory synthesis. Next, after CTS, what we have? Routing. Routing means I have to connect the cells by using what? So these cells we have, right? These cells I have to connect by using metal layers. Now you can see the metal layers, right? All these metal layers are connecting what? Used to connect the standard cells. You can see the routing here. All these are metal layers. So connect all the standard cells by using this what? Like this metal layers is called as what? Routing. Right? Connect all standard cells by using metal layers. This is called as what? Routing. Next we'll see what are the checks after routing, right? We have to follow the DRC rules. We have to see whether there is shorts, there is opens. So we do all these things. Routing. After routing, we do sign off checks. So after routing, we see checks after routing. If there is no problem in routing, right? Then we do what? Sign off checks. Sign off checks means, see, each stage we have done STA. After CTS, in CTS checks we do STA, like setup and hold check we do. In the final stage again we do setup and hold check, because this physical design is done by using a tool called as ICC2. Sign off checks in ICC2 also we can do setup and hold check. After placement we do setup and hold check. After CTS we do setup and hold check. After routing we do setup and hold check. But ICC2 is not very accurate to do this. There is an accurate tool called as what? Prime time. Prime time. So by using this prime time, what we do is we are going to do setup and hold check. Prime time and star RC. Star RC. By using this, we do timing sign up. This is done hands on. Use prime time. We use what? Star RC. We do timing sign up. Means setup and hold check we do in prime time, and we fix the issues if there is anything. Then we do IR drop check. It is theory, we don't have license for that. IR drop is theory, because Redoc, the tool used is Redoc, and we don't have Redoc tool. Next is physical verification. So in physical verification, we are going to verify all the rules given from foundries met or not. If all the rules are proper and everything is met, then what we do after all these three sign off checks, we give our GDS file to the full chip level engineer. We'll give our file to whom? This block level design we give to what? Full chip level design engineer. Full chip level design engineer, he incorporates in full chip. Our block is going to incorporate in what? Full chip. He will do his checks, all the checks, whatever he want to do, he will do it. After that, he will take GDS of this entire chip. He will give it to what? Foundry. So these are the steps, these are the topics covered during the course. So theory will be done on Saturday and Sunday for all these topics. Parallelly, you will be working with lab in Monday to Thursday classes or in the weekend classes. So this is how it looks, right? Your physical design looks like this. So you can ask me if you have any doubts. So from next Saturday, the first topic starts. From next Saturday, I will start with cell delay, power consumption. Even it's already done. I will not do the same thing. I will do a little bit different. Like what do you mean by drive strength? What do you mean by HVT, RVT, and LVT cells? How do they affect the delay and how do they affect the power and area? So all those things will start from next week, next Saturday. From the Sunday, we start with input files required for physical design. From next Monday, the lab starts, but not next Monday means it's not tomorrow. Next to next Monday. From next week, you have tool installation. I think it will be on Wednesday and Thursday. Admin will inform you. Probably admin is planning to split this batch into three because we have 90, almost 90 students. The batch is split into three batches. So probably they may initiate that process next week. How to split into three batches. Because we cannot do all the students at a time. Theory can be done like how I'm doing now, but lab cannot be done because lab we should give importance to all the students. In 3 hours we cannot clarify doubt of all the 90 students in the lab. So we are splitting the batches into three batches. So probably the theory we have planned for Monday, Tuesday, Wednesday, Thursday, right? 4 days. We may cut into 3 days. Three batches, one batch Monday, Tuesday, Wednesday. Other batch Tuesday, Wednesday, Thursday. In one more batch, it will be like some other day. Like that day, he is going to change the batches. So admin will talk about that. So that may vary. So instead of 3 days, generally we used to have 3 days, but it will 4 days, Monday to Thursday, lab. That may change to 3 days. Yes, I have done. If you have any doubts, you can ask me. If you don't have any doubts, you can go. You can do, but any doubts, you can ask me.
What is the role of analog design engineer?
What is the rule?
Analog design engineer. What they will do?
I am not sure. What is that? What is the name?
Analog design engineer.
Envelope.
Analog.
It is in VLSI only. I don't know. I'm not. No, I'm not.
So there is also one branch. DFT is there, physical design is there, DB is there, and another one is there. EDE.
Unlock design engineer. That is full custom. Yes.
Okay. So what is their role?
Unlock design engineer. Sir. That is not part of ASIC design flow. That is
Okay.
they work from the scratch. Like
Okay.
see, every design we cannot implement by using Verilog code. So I cannot write the Verilog code for amplifiers because that is analog circuits.
No.
If I want to implement amplifier or differential amplifier, or if I want to implement op-amp, I cannot implement by using this flow because this flow starts with what? Verilog code. So we cannot write the Verilog code for
PLL
uh,
and OPAM and
op-amp and all. So they will design those things from the transistor level. So those that is called as full custom design.
full custom design. And this one, what we are doing is the ASIC,
ASIC flow.
ASIC flow.
Mm.
But we require that one also, not sir. Means we require the custom.
And custom files will get. So they will draw the layout. For example, I told there is macros, right? We directly reuse the macros. See, this macros SRAM is done by ASIC flow only, but PLL. PLL in our IC we even need a PLL also. So that those engineers will work on how to write the schematic for PLL from the transistor level by using different W while ratios. They will work on how to write the PLL schematic. After writing PLL schematic, there is a layout team. They will draw the layout for PLL schematic. After drawing the layout, we take GDS file from that team and we take LEF file. We incorporate in our physical design. So in physical design, we have even files from them. I am not designing PLL. I'm already using, as I'm using macro here, this macro, I will reuse the PLL what they have generated.
Oh, okay. And then, sir, did they use any tools for designing these things?
You're talking about full custom, right?
Yes, sir.
Yes, they will use the tool. Like in Cadence, they use uh, Virtuoso, and in Synopsys, they use custom compiler. They use some tools.
So, sir, we are dealing with it in gate level, and they will be dealing in transistor level.
Even this NAND gates, AND gates, right? I told standard cells. I told this is the layout of standard cells. Who is going to give the layout of the standard cells? This is a layout of standard cell. This layout of standard cell, who is going to give? From we will get from those files. We'll get from that team only. So there is one more team, what is called as full custom team. Again, full custom team is divided into design team, layout team. Right? They will do all these things. They are responsible for that.
So,
Library characterization team. So there are many teams. Again, how we have in ASIC flow, right? They have many teams. Full custom design. Standard cell development team, analog layout design team, standard cell layout design team. So there are many engineers like that. Yes,
so which one is more complex? Means the custom side or this ASIC?
see layout. See again, when I come with custom, there are two things: custom, full custom design, full custom layout. For example, you told PLL. PLL has to be designed. PLL means I cannot use transistors however I want, right? I used to connect the transistors in such a way that it's going to implement the action of what? PLL. Without INL, without DNL, differential nonlinearity, without integral nonlinearity, without noise. I have to implement the PLL. That is called as what? Full custom design. There is a full custom layout. The role of full custom layout is see the schematic, how the design is done. Further to draw the layout. Full custom layout is easy. But full custom design is complex, very complex. Then you have to learn the concept of MOSFETs, mixed mode signal analysis. So how this op-amp gain is dependent. It depends on what parameters. Op-amp bandwidth is dependent on what parameters. How to change the bandwidth, how to change the gain, how to implement, how to use different W-while ratios, how to do biasing. Biasing means applying DC voltages for amplifiers. All those concepts you have to learn for that.
So they also done with low power design.
Low power design everywhere is present. You can also implement low power design. Low power design means turn off the circuits whenever it's not required. See, only thing is we deal with plenty of cells. We deal with lakhs of cells because we are not worrying from the transistor level, directly worrying from the gate level. But they do from the transistor level. They cannot do the design for lakhs of cells. They do only design for only hundreds of cells. In a design, there are thousands of cells, it's very difficult them to draw the layout. Layout is also drawn from the level of scratch. From the transistor level, they draw the layout. But in physical design, what we are doing, we are directly reusing the layout they have drawn. We are not going to draw the layout. They have drawn the layout, they have given the files for us, LEF file and GDS file, we'll directly reuse it. That is purely full custom design, they will support for us.
So we require demos.
Company has that teams. It depends, right? It is not every company should have that. They can also purchase it. The files they can purchase from some other company. They can do that.
So this my software should have told.
Hmm.
So will they tell the installation of the software individually for?
1 second. Online students, if you don't have any doubts, right, I will end the meeting. Okay, thank you everyone.